Hello, everyone. I have to say that you will love this object. It's unique among planetary nebulae, mainly for its recently acquired Borja nature. And what it's a Borja planetary nebulae? Well, all of us know the usual path of the planetary nebula in the Heston-Russell diagram, first in its horizontal path, and then in the current track to die. But in some special cases, the central star built an outer layer of helium, which reached the critical mass to ignite and produce a very light thermal pulse. This event ejects to the medium highly processed and hydrogen processed material at high speed. As a consequence, the central star gets cooler effective temperature and come back to the point where began its post-AGP evolution. So in that sense, have born again. Our main character in this session is HuBi, and it is in that point on the Heston-Russell diagram. But who is HuBi? Well, in the first works we labeled HuBi like this was Hu and Gibo in 90s. This is the optical spectrum. Then Pollack and Hill reported the double share around the central star and the high and low density. Now we know it's grown. Then was Leuhaven and Hammond, which measured the effective temperature of the central star, about 30 kilocalds, and its composition, with a special attention in the composition of the hydrogen. Then Payne was the first to say Borja event in this object, but he chose the other option, a slow evolution from a low star, AGB star. And was in 2018 when Guerrero dynamited this object, throw again the hypothesis that HuBi won't have suffered a Borja event. And what led Guerrero to say that HuBi won't have suffered this type of thing? So three main reasons. First, its peculiar structure of ionization with the low ionization species on the inner shell, when usually are in the outer shell, as you can see in this image. And the outer shell of HuBi are recombining. So another reason was that its photometry had changed a lot over the years. The central star had dwindled by a 10 magnitude in less than 50 years. That's so much. And finally, the detection of the helium-2 emission line. Remember that the effective temperature of the central star was 35 kilokelvin, so it's enough to ionize this line. So we need another source of ionization. It's our many rarities to throw the hypothesis that carbon reached high-speed ejecta occurred at least 50 years ago. I repeat, at least. So we need to confirm 3 facts to corroborate. As the first one have been already confirmed just 1 year ago by Borja Garcia. As you can see in this image, the slides the velocity, and she discovered a fast expanding shell in the nitrogen 2 lines, which reached speed at with velocity rise up to 300 kilometers per second. Second one, there are a few words which confirm that the gas is cooling fast, and recombining. And the last one is what we want to confirm in this work. So to carry out this, we have used 2 different instruments or series to produce long slit spectroscopy and Megara with IFU observation, both in GTC. And in this image, you can see the field of view of Megara and also the aperture used to extract the spectra from Osiris data. Let me to show you the first result of our work is the tomography of HuBi, and in the left side you can see the emission purely internal, such oxygen-3 and helium-2 line, that it's so clear the detection of this line. In the right side you can see the H alpha and H beta, and also helium-1, which have emission in the outer shell, but this 2-1 has also emission in the inner shell. I will show you this in 1 minute. And finally, there are lines which has emission from the inner shell and also from spread emission from outer layer we label as intermediate shell. So the high spectrum resolution of Guerrero have allowed to us to extract or separate the emission from the inner shell to the outer emission for the first time. So we have carried out two methods to do this. First, high velocity component isolation and multi-junction field. And we have used one and another depend on its advantage or disadvantage. The high velocity component isolation produces smoother maps, but the selection of the spectral channel are different. So we have used to a map of extinction, and the other one produce flux value more reliable. There are two noises, so we have used to calculate pseudo-slit support analysis of the Osiris data. I will show you the reason for this in a while. Just let me to show you the another important result. First, the left side, the map of extinction. In previous work, the extinction of Borja was similar, but with the both emission clearly separate. The extinction of the inner shell is almost double than the outer extinction. And in the right side, you can see the BBT diagrams. To be discussed the BBT diagram in the case of planetary nebula are reliable or not, but you can deny that ball shell has two different sorts of ionization. The outer shell is located in the zone of photoionization, and the inner shell is located in the ionization by shock. Also, the Osiris data in green fit fairly well with the negative data. So we just need to measure abundance to confirm our hypothesis of the Borja event, and it's essential to take into account a shock in the model. So this is the spectra extract from Osiris, and each line in this spectra had been treated different depending on each purely internal, purely external, or mixed emission. We compare this line with Guerrero data, and the key fact of this data set is be aware about the differential chromatic refraction. In this image, you can see the slit of Osiris placed on the middle of the image, and the emission profile of nitrogen-2. As we move at lower wavelength, the slit is located in higher up. So the effects, and in the emission profile, you can see the one peak emission profile. The effect of the chromatic refraction are not disabled, so it's meant to be corrected. Likely to us, the DRSC effect remain practically constant with whole observation. So we have placed, to correct it, we have placed a silver slit onto the image. That's one. The image, and this here corrected position of the Osiris slit for each line, and we have used the map I showed you before. With this method, we obtain the true radius in different places for some lines, but are the true radius. And we are ready to obtain the abundance. We have carried out this calculation with
2 minutes.
mappings. Thanks. With mappings, and during the whole observation, the effective temperatures are the same. The shock parameter assumed at the beginning were these, and we have used an iterative process to calculate the movements. First, we vary the oxygen and nitrogen abundance with a special attention in this line and fix the abundance, the helium abundance. Then we fix these two abundance and check it if these abundance are well. So we vary helium abundance and check it that fit very well with our radius. And finally, we check shock parameter assumed at the beginning. First, we vary the velocity, we fix the abundance, and finally, we fix abundance of velocity and vary the pressure density. So these are the parameters of the best model for our object. Sadly, we have some issues with underestimate the oxygen 2 line and overestimating the helium 2 line. And we expect to correct this in the next work of Q1 about the dust. So this is the summary of the work, and I want to repeat the last sentences. So the abundance obtained by using mappings are in agreement with Borja scenario. So thanks all. All your questions are welcome.
Okay, thank you. Please raise your hand. Do you have questions? I was curious, what is the observational evidence for the fading that over the 50 years?
We have taken over the year, first in 96, and we can see that in this image, that's the magnitude. It's
so those are from this. That's from the spectra. Okay.
Yes.
I don't see any hands up.
There is also some information on photometric observations in the TSS and other sources, Howard.
Oh, okay.
Can you please show again the image that you say you separate the shell?
Mm-hmm. This one?
Where you see the big picture. What is the outer shell was ejected before the born again eruption outburst?
Yeah, of course.
Okay, so what was ejected now is the inner part. Can you show it again? You see both?
What? Repeat?
If you can show the largest image you have of this planetary nebula.
In this image of this.
Yes, the image. If I didn't have time to see the previous one. Oh. This one?
Yes.
Okay. So it's a little bit elliptical. This is what.
This is spiral-like.
It's. Excuse me.
Spiral-like. It's like.
Yes. Okay.
Like,
so yes, we can see an axis here.
Yeah.
So what I see here in the green part, what part was ejected in the born again outburst and what's previously here?
The inner shell. We thought that it's the inner shell. also spread emission. Pay attention
Okay.
that it's likely produced to the volume.
Yeah, you can see the axis here somewhere. We see here, and something here. But in inner part, I don't know. Can you resolve the asymmetry of the inner part?
The inner part in this image. In oxygen, you can see that the axis is around of the 50-degree, more or less.
So now the axis is in different direction relative to the outer one.
Yes.
So it's interesting to check it as well. Yeah, very good, very nice. Thank you.
Are there any more questions? If not, if you could stop your screen sharing and